Yes, all they're just some ideas to be thrown out on things that you might potentially be able to do with SDN. We'll talk about the blank box, the box at the top of block diagrams. You look at almost any SDN block diagram, there's a big empty box at the top, and we'll explain that. And then we'll discuss what you guys think of all this. So the big buzzword in the industry, cloud computing. Some people still say that cloud is a real thing. I don't know how many of you have seen the sticker before. Some of you are familiar with it. There is no cloud, it's just someone else's computer. But it's not the whole story. Saying it's just another computer in a remote data center isn't enough. When we're talking about cloud, we're really talking about orchestration systems. We're talking about pools of resources, not just a single box. We're talking about storage, compute, networking, and the ability to have some sort of multi-tenancy in a cloud data center, for example. And the last point is the important one. We don't care about the physical. When we're talking cloud and we say throw it in the cloud, that might sound really generic, but really we're just saying, I don't necessarily care what computer this thing resides in. So how's it relevant? Well, the classic definition of SDN, as proposed by the Open Networking Foundation, who handles a lot of the open flow stuff, the physical separation of the network control plane from the forwarding plane, where the control plane controls several devices. Is it vague? Yeah. Has it been morphed by our industry? Absolutely. Is it entirely meaningless? Debatable. So let's clarify. So to be clear, SDN is not a technology. It is not a product. It is not a protocol. It is not a technology. It's a concept. We use technology and protocols and products to bring together our networks into an SDN solution. But, there's always a but. All of our vendors seem to have skewed this definition. They all have their own idea of what an SDN strategy should look like. Some of them follow the original definition fairly closely, the separation of control and forwarding. Some of them not even close. And it's become confusing. What is SDN? What isn't SDN? I actually had somebody ask me, well, if BGP is used for control plane in SDN, then is BGP SDN? Well, no, it's not. But it's a piece of the puzzle. The vendors aren't helping this at all. They've all got their white papers talking about SDN. A lot of it is nonsensical and has nothing to do with SDN. But they're calling it their SDN solution anyway. But because of this, we're classifying SDN into one of three flavors. The first one we call Open SDN, and this is what is most closely related to the original definition of SDN. In this case, we have the complete separation of our control plane from our forwarding plane, with some sort of protocol speaking in between them. Typically, this is OpenFlow. It utilizes some sort of central SDN controller that handles all of our control plane information. Our forwarding elements are simplified. You could have a switch that is nothing more than a couple flow tables. Again, the southbound interface protocol, usually OpenFlow, is what is the protocol between the controller and the forwarding element. And there's a lot of companies that are coming up with products that fit this solution. Under the commercial list, Brocade, Big Switch, NEC, HP. NEC was the first commercial controller on the market. In the open source world, we have big projects like Open Daylight and smaller open source projects, Riot, Docs, Trima. These are all small controller implementations. Our second definition, SDN with overlays. This might be something that would be a little more familiar and useful to those of us in the data centers. This is where we actually have our control plane is still separated from our forwarding. It still sits in its own controller. However, all that's really doing is installing some sort of shim in our hypervisors. Juniper calls it a vRouter. And we're building tunnels between these vRouters. So we can have multiple boxes with their hypervisors and have full connectivity across a physical network. The tunnels are one of many protocols, the most common being VXLAN, GRE, NVGRE, and EVPN is becoming more and more popular. Because of the ability for these vRouters to actually use routing instances for those familiar with Junos. This allows multi-tenancy, complete separation of our tenants. It does not address the underlay though. So we still have our physical network that isn't changing at all. So we need to make sure we do something with that. Our northbound interface, we have APIs to talk with our controllers so that we can have some sort of programmability. That's a really key aspect of SDN in general. Our southbound interface varies by vendor. In Juniper's case, its controller talks to the vRouters using XMPP. Some people might be more familiar with that as Juniper. But really, it's just a messaging protocol. We're just utilizing it for control plane information. A few different vendors are doing overlay. Actually, a lot of vendors are doing overlays because it's such a simple, relatively simple thing to do in the SDN space. Juniper Montreal is one, of course. VMware NSX is an overlay. PlumGrid and Nuage Networks. Nuage actually it works very similar to Contrail, except they actually handle the underlay as well using overlay. And they can correlate between the overlay and underlay. SDN by API. So basically, this third category is not something we actually want to call SDN, but the vendors are calling it SDN, the vendors who produce these solutions. So we have to include it. Really all we're doing is we're taking our traditional networking element that has its regular control and forwarding plane, adding an API on it. That's it. That's all we're doing. And there are some vendors that are doing solutions like this. So hopefully that clarifies what SDN is as far as the actual implementations and what vendors are doing. Again, SDN definition has been heavily skewed over time. But why do we need it? This is a quote I dug up a little while ago, and I think it's really relevant. In this business, we shouldn't forget the purpose of the network to serve the needs of the application, and the network stopped doing that a while ago. We've got to a point with our networks where we're just building really big networks and just hoping that whatever application we throw on it is going to work. That's what we've been doing for at least a decade. That needs to stop. It's costing too much money, costing too many resources, and there's really no reason for it. We need our applications to start talking directly to our network and having our network react to our applications rather than being proactive. So a little more detail on this. Traditional networking does certainly have some issues. High operational costs, as I mentioned. Difficult to manage, scalability. Decentralized, monolithic software. If we want to upgrade our OS on our iOS device, it's a single binary, traditional iOS device. So that brings the box down. Even in the Junos world, which is FreeBSD packages, you still never just upgrade one package at a time, let's be honest. We're going in there, upgrading the entire OS, rebooting. We're doing a lot of over-provisioning for worst case scenario. Again, we're making our networks really big and beefy, hoping that in a failure we still have enough capacity. Layer 2, Layer 3 load balancing. Far from perfect. In Layer 2 world, we're talking about spanning tree. We can do some cool things, sort of cool things. Multiple spanning trees, we've got multiple root bridges, and then we have multiple paths. But again, it's very proactive. There's no traffic engineering aspect to spanning tree. When we're talking about Layer 3, equal cost load balancing works very well. Unequal cost load balancing doesn't work very well. And non-best path forwarding requires some sort of static configuration, whether this is a simple static route or some sort of RSVP traffic engineering, for example. If we want the traffic to go down the path that the IGP has not selected, we need to force it that way. So our networks have issues. How can SDN help this? So it starts in the data center. The data center is the most obvious place for all of this SDN stuff, primarily because of the overlays. Overlays are a really simple way to get started with the world of separation, control, and forwarding. They solve an immediate need. Tunnels using VXLAN, EVPN, MPLS over GRE in the case of Contrail. These can all solve immediate issues. They allow things like data center interconnect. If you wanted to do EVPN, tunnels between your V routers, between data centers. You now have L2 between data centers. Routing instances, like I said, routing instances on tunnel endpoints, VTEPs, virtual tunnel endpoints. They enable our multi-tenancy. These allow us to have many customers in our data centers all using the same hardware. SDN complements existing orchestration platforms. For anyone familiar with OpenStack, something like Juniper Control works directly with OpenStack. In our data centers, we have an increased focus on east-west traffic for applications. Gone are the days of sending all of our traffic northbound to a big, beefy central firewall. That's really inefficient. Instead, microservices are becoming more prevalent. So these are small little VMs that we spin up, each with its own dedicated purpose. And we can throw virtual firewalls in front of each of these. So then we have a firewall with 5 rules on it, instead of one big beefy firewall with 10,000. But the programmability and automation of these types of applications are really the key for data centers. And the network needs to be reactive to the applications running over it. We need to be able to reallocate bandwidth according to our applications. What about the underlay? So we've been talking about overlays. The underlay itself, it remains unaffected. And it's irrelevant. So we have to make sure that it's irrelevant to the overlay. So we still have to make sure that the underlay does not become a bottleneck. So L2 networks, as we know, don't scale well enough. We're using awful, horrible protocols and spanning tree to make sure L2 networks keep us free from loops, but at the same time robbing us of our bandwidth. Class IP fabrics. So we're talking full-on BGP IP fabrics. Allow layer 3 equal cost load balancing, but that's still not dynamic enough for us. The underlay may be a good place for OpenFlow. This solves the issue of our network not being dynamic. Some vendors handle the overlay and underlay and correlate the two. So these are some of the vendors that are doing some things like the tunnels between V routers, but they're also handling OpenFlow on the underlay, and then correlating the overlay and underlay together. It's really slick. The WAN is a good place for SDN. Traffic engineering in our WANs right now. Very proactive. These are things that we're configuring ahead of time. Yeah, we can have as many backup MPLS paths as we want for our traffic, but it's still manual configuration. With SDN, we can do reactive traffic engineering from a central controller. We can actually have our controller telling the devices around it what path to take. When we have some sort of failure in our WAN, we can actually have a central traffic engineering device signal to all of the devices on our WAN their new path. We don't have to wait for it to reconverge. It eliminates over-provisioning, because at this point we're only using the bandwidth we need. We don't need to have a whole bunch of huge pipes for only a little bit of traffic, just hoping that if there's a failure, we're still okay. Google is a good example of a company that's actually doing this right now. They've actually got a central traffic engineering server set up that really all it's doing is telling all of its WAN devices what direction to go in. So instead of having a lot of static path entries in its MPLS network, instead it's telling each individual device what path to take across the network. So we don't have any worries of convergence and reconvergence. So we're talking about OpenFlow. Let's take a quick look at OpenFlow, how it works, what it's used for, but by no means comprehensive. My boss, Doug Marchke, actually wrote a book on OpenFlow. I really suggest you take a look at it. It's a really good overview. OpenFlow oversimplified. I apologize for it being oversimplified. We just don't have enough time. The idea with OpenFlow is if we started over with our networks, how would we build it? If we could go absolute clean slate, which was the name project that this originally started. If we could start over, what would our networks look like? How would we build them? Well, they decided that they would have some sort of centralized control plane and a distributed forwarding plane. And then they would need to have some sort of protocol, obviously, talking between their central control plane and their distributed forwarding plane. And they came up with OpenFlow. So OpenFlow is really just a messaging protocol. It enables programmability of the forwarding plane. So it can use any sort of APIs, any programming language that you're familiar with to actually program these flows directly into the switches. Our forwarding elements at this point can run in one of two modes, either OpenFlow only mode, where it runs just OpenFlow and that's all the only instructions it can take, or hybrid mode, which is something that we're probably going to be seeing for at least the next decade, probably, where we actually have our devices that can take OpenFlow instructions, but also run as a traditional switch as well, as a backup, or certain ports can run OpenFlow, certain ports don't. So taking a look at flow matching and how our matching actually works for creating our flows. OpenFlow versions before 1.2, so 1.0 and 1.1, used simple match fields, really basic stuff, ingress port, MAC source, MAC destination, IP source and destination, IP protocol, source destination port, really basic stuff that's in the IP header. Versions 1.2 and above use TLVs. So instead of matching on these individual fields, it actually has a TLV for each individual field. So that's a type length value. For anyone who's familiar with ISIS, that should be fairly straightforward for you. But basically, it's very simple. If the packet matches, perform the specified action. If it doesn't match, you can either choose to drop the packet completely or forward it to the controller for more processing. So on our switches, we have flow tables. These are a prioritized list, top-down, executed in order. First match is executed. These aren't longest match, like IP lookup, for example. And each of these flows has timeouts, either idle and hard. Idle timeout is exactly what it says. If the flow is idle for long enough, it gets pulled. Or hard timeout is absolute lifetime. So our table looks something like this. It's a little bit oversimplified. Basically, our match fields and our actions with some stats and timers. Pretty simple. So let's take a look at some examples of how these things actually match. Again, we're looking at something that would be an OpenFlow 1.0, 1.1 because we're matching on simple fields, but it gives the example, makes the example work. Simple one, ingress port. Packet in port 3, send it out port 5. Simple. Destination MAC address, output port 23. So this is kind of emulating standard switching behavior. IP destination, output port 82. This stuff really couldn't be any simpler. Some slightly more advanced examples. With that source MAC, drop it into VLAN 22, and then forward. If it's in VLAN 85, give it priority 7. This stuff is really simple, just a match in action here. In this case, an IP packet that's TCP 80, give it TOS value X22. Pretty simple stuff. How is it useful? How can we actually leverage this in our real world? So what can OpenFlow do in theory? Well, again, this is where we're talking about things that you should take with a grain of salt. These are just ideas. L2 or L3 routing, no longer an issue. Do we need spanning tree if our network can no longer have loops? If each individual device is signaled from a central place, there's no possibility of loops. What about layer 3? Do we need routing protocols on our network, like OSPF, telling us what path for a packet to take? If we have a device that has a central view of the entire network telling each individual device what path to take, is that necessary anymore? Now, I'm not saying to get rid of spanning tree or OSPF. That's a long way away. But you can see the idea. Applications that forward to multiple endposts are inherently supported. When you have an action on an OpenFlow packet, you can tell it to go out more than one point. What's that emulating? It's basically multicast. So I'm not suggesting these things are going to happen immediately. But that really leads to the final point here. We need that killer app. When we look at this kind of block diagram in the SDN world, we have our SDN controller in the middle. We have our network elements at the bottom with our separated control and forwarding planes. We've got our orchestration system. That could certainly be OpenStack. It could be a lot of things. Our management device, management platform, that could be anything. The thing we need to figure out, though, is our applications. The applications at the top are what are actually going to make SDN come to life. They're going to be what provides a business case for actually doing this stuff. Without some sort of applications pushing SDN into our world, there's no real business case for it. OpenFlow is very cool in an academic way. But what we need is to have people, really, really smart people, Silicon Valley kind of people, San Francisco kind of people, to write something for this. There are some companies out there doing some cool stuff with OpenFlow. But we need application developers to really step up and figure out cool things to do with this. How they can have their business applications that their actual, what the company is making money on, their applications running over their network. We need some sort of application that ties that into our physical network. What if we had some sort of application running across our WAN, some sort of business application running across our WAN, and we were to build something on it that could program OpenFlow switches directly through some sort of API? That would be really useful. So, just to close this up a little bit, overlays are a great solution in the data center. They're fixing an immediate need. They're really useful right now. But they don't address the current underlay restrictions. So we still need to figure that piece out. We're not really fixing our physical network at that point. OpenSDN with OpenFlow, our centralized controllers, those sorts of things, they do show a tremendous amount of promise, but they require a really open mind. I mean, I just suggested to kill OSPF. You need a pretty open mind to consider that. There are ways to go about it in a phased approach. Again, we can run these switches in hybrid mode. We can start building some cool applications, SDN applications that sit on our OpenFlow network that don't necessarily have to impact our business critical applications yet. We still need to fill in those boxes at the top of the diagram. We need that killer app. Somebody write it. I'm not smart enough. We're still a ways from mass adoption by all accounts. Realistically, well, overlays are ready for now. A lot of people are deploying things like Contrail and NSX solutions with overlays. The OpenSDN stuff is still really needing to pick up. It's a while off. Again, because we don't have those killer apps. We don't have a really, really good business case yet. Right now, all we have is cool ideas. Automation is a precursor to SDN. Automation is going to get us to where we want to go. This is going to get us programmers who are fluent with networking and are merging with the networking aspect with the programming aspect. I know when I went to college, I took networking because I didn't want to be a programmer. It was one or the other. So for me, seeing that world coming together is pretty difficult. But these kids growing up now, coming out of college, they need to really focus on this stuff. A network engineer is going to be a programmer. It's going to be the same job. And of course, our good friends in the DevOps movement are the ones leading the charge on this. These are the guys who are actually writing automation tools for our SDN applications. So I'd like to hear your thoughts. Not your everyday QA. I want to see where this stuff could be useful to you. I want to hear if you think it's stupid. Say it. If you think it's completely worthless, go ahead and say it. But I want to hear where you think you might see this going into networks going forward. Anybody? Yeah.
I'm just curious, how does high availability work with centralized routing?
So the question is, how does HA work with a centralized controller? The fact is that's really vendor dependent. Some things are peering with BGP for control of state information. Some things are actually using some sort of proprietary protocol between controllers for HA. Some places have deployed SDN controllers in a hierarchical mode where they have a couple controllers doing different functions and then one large central controller that handles all of them. There's a lot of ways to go around it. As far as protocols go, though, it really depends on the vendor.
So you brought up the point that, okay, if you have like a centralized user network who needs, spanning trooking with the OSPF, but
Sure.
wouldn't you still have convergence issues and pushing down, a centrally generated set of configs to hundreds and hundreds of devices?
Right.
So how
So,
do you get around that?
so the question there is basically latency with the controller,
Right.
right? Yeah. That's still an issue, actually. That's still something they're working on. Obviously, your network, your underlay network, between the controller and the forwarding elements has to be pretty rock solid. But that's definitely still a concern, even now. And why this is probably not going to happen right away. There's a few things. Security is another one. A lot of the open flow stuff has been written without the inherent security that it might probably should have. So they're working on that too. But the ONF, the Open Networking Foundation, check out their website. It's really great for resources. But you can see a lot of working groups working on all of this kind of stuff. Anybody else? Yeah.
Yeah, so you kind of said that we're still waiting for the kill wrap to take advantage of something like networking.
Yeah.
But absent that, do you see, like, if you just do a drop-in replacement of existing networking technology with software-defined networking, do you see a performance hit in software-defined networking?
So the question is there going to be some sort of performance hit if we do a drop-in replacement of SDN into our tradition, as opposed to our traditional networking? Well, hopefully no. That's the idea. Again, the latency issue comes into play there. The idea of a centralized controller sitting in the middle of our network with hundreds or thousands of forwarding elements all talking to it becomes a bit of an issue. Another one is the sizes of flow tables on switches. Right now, our switches just can't handle the size of flow tables that are required for mass deployment. That's coming. So, is there a performance hit? Ideally, no. Right now, probably, just because of our hardware. Does that answer your question well enough? All right. Yeah.
Do you see OpenFlow supporting stateful behavior or session-based behavior at some point?
Is OpenFlow going to support stateful behavior? No. It is a TCP connection as far as the connection itself, but the messaging is definitely not stateful. It's very much a pushing the flows to the device, and then they either age out or get pulled in. Yeah.
How easy to drop in something like OpenFlow when you don't own the data center networks, you're on Amazon, AWS? I mean, you have the ability with VPC to have ASM, but how do you sort of implement that when you own your own competing resources?
So how do you implement SDN in an environment where you don't own the infrastructure?
Yeah, it's not your data center.
The data center. So you could, if you're working on, let me think of how to say this. If you're doing everything within compute, if you're doing virtualization, things like that, you can do something like control overlays. If you wanted to do OpenFlow, then at that point you're looking at doing something like Open vSwitch, which supports OpenFlow. But if you don't own physical hardware, you're still limited by that. So that's a little tougher. At that point, you just hope that everything's virtualized and you can go about that route. But again, that's why in a data center, the overlays right now makes the most sense. Because it doesn't address the underlay, but in your case, you don't control the underlay anyway. So as long as that's rock solid, you should be okay.
Do any of like the current network element vendors, the hardware providers, provide any sort of like sandboxing function where you could sort of have a section of the device, let's say Amazon could sort of open a section of their physical hardware and provide constraints around it so, customers can't fork the entire AWS cloud, right? Is there anything going on in that area?
I don't think so. I know that you can run switches in hybrid mode, which sort of accomplishes that. But if you wanted true segmentation, not really. I don't know of anything that does that. That would be a really good solution for someone to come up with, though. Absolutely. If someone went out there and bought up some white box switches and ran something like PK8 on their switches, where they have full control over their OS, then they can sandbox whatever they want. So that might be, if you're a programming type, something you could look into. Yeah.
Could you go over a couple of the really high level cool business applications that have been written yet? Like maybe a hypothetical for DDoS or someone in the network, something like that.
Hypothetical applications that have been written. So that filling in those boxes.
Cool use cases, yeah.
Cool use cases.
Just high level.
I don't know. There's so many. There's the potential is there. I don't know if I was smart enough to create that killer app that I'm doing. Right? But as far as business applications and business cases, people have been doing some cool things with OpenFlow. Like I mentioned, Google has done it in the WAN, so they've got their central TV server. That's one of the big ones. Another example is you could do in an enterprise or a campus environment. If you're in a university campus, for example, actual campus, you could do something where instead of using 802.1x for authentication, you use OpenFlow and forward unknown MAC addresses to the controller, which checks your database of users instead. That's something that could be done. Creating blacklisting applications, things like that. We actually, in some of the classes we offer, we actually have get to play with some blacklisting stuff. But you could build a pretty cool NAC solution with OpenFlow.
You could also do something like where you're monitoring traffic and performance. You get into a high frequency trading kind of situation. You can adjust the routes based on best path, performance jitter, whatever.
Absolutely. So if you're able to tie your business system directly into your switches, you can start allocating bandwidth dynamically across the network. How exactly that would look? Yeah.
I worked for an ISP before. We had rooms full of people manually telling them into Cisco switches and doing stuff on iOS, and it was a nightmare.
I'm sorry.
The configuration drifted apart from the actual accounting, would screw stuff up and make mistakes. Sure, just having the API to all that.
Right, and that's the big thing with all of this is having that open API. In a lot of cases, it's a REST API sitting on the controllers. The ability to have some sort of self-service portal where if you need to make changes, you can do it in. As network engineers, it's kind of turns me off a little bit. But the idea of having some sort of graphic interface where you can actually reconfigure. If you need a new BGP pairing to customer A, and you just click BGP pairing plus customer A. You don't care how it actually happens. And if we could get things to a point where that actually worked in a scalable way, then that would be really useful. Instead of telnetting into thousands of boxes to make it happen. If you're talking about a full WAN, if you have 1,000 nodes on your WAN and you want to add a new tenant, it's how many boxes you're touching. You do it through SDN, central server. It's easy, it's done in 2 minutes. Anybody else? Yeah.
In your breakdown, you have sort of the classic OpenFlow SDN case, and then in the last one you have the Cisco case where they're basically just putting an API in front of the box, right? But if that API is sufficiently rich and pretty much allows you to do anything that you could do from the CLI, what can you actually do with SDN that you couldn't do with that?
Right, and that's kind of their idea. I sat in on presentations from that vendor where they're talking about how SDN isn't useful, but their product is. In other presentations, they say their product is SDN, so a little bit of mixed messaging there. If it's a sufficiently open API, you can do a lot with it. And I think that was the idea, is to have an API across all of their various platforms with very different CLIs, where you can have a programming layer on there and be able to do whatever you need it to do. What can SDN do that on top of that? I think programming the hardware directly, the forwarding layer directly, I think is a big part of it. The fact that that API, really all you're doing is giving the ability to configure your devices from a central place, but you're still configuring the device. There's still a configuration file on the device. So you're not really removing that layer at all. So you still have your distributed control plane. You still have to have protocols. I mean, again, I'm not suggesting a world with no SPF, but in that solution, you still have to have your layer 3 protocols delivering information between devices. Control plane isn't centralized. So it's great from a programming aspect, it's great from a configuration aspect, but really it's not a whole lot different than, say, Cisco Prime, where you're doing central management anyway, for configuration. You're just doing it in more of an open way so that people can actually write programs. So it's great for automation, no question. I think SDN has a few more layers on top of that. Anybody else? All right. Thank you guys very much.
Thank you for coming out. We like to end with community announcements, so if anybody wants to make one, we're looking for one of 3 things. If you're looking for a job, there's a lot of people in the room that are hiring. If you just launched a project that you want to share, you're welcome to talk about it briefly. Or if you're working on something right now that's giving you trouble, like you've got your laptop and can't figure out a firewall rule, you can come up and ask for help. There might be someone who can help you. Do we have any of those types of announcements? Our next meetup is going to be in 4 weeks at gandhi.net, which is an awesome domain name registrar. And so please check out the meetup group for details on that. And besides that, thank you for coming tonight. Thank you to Juniper for putting together this awesome talk. And thanks to Chartboost for hosting here at their amazing space.
Yeah.